So let's work on some practice problems about hydrohalogenation of alkene. We have an alkene reacting with HBr. In the first place, the double bond of the alkene will act as a nucleophile and grab the hydrogen. Then the bromine atom will act as a leaving group and leaves. Here it is. In the second place, we have two carbons missing one bond each, since we used to have a double bond here, and here we have a single bond, so we are missing two atoms. Here, according to Markovnikov rules, the hydrogen atom goes into the less substituted carbon. Here we have a secondary carbon since it's linked to two atoms, and a tertiary carbon since it's bonded to three main atoms. So the hydrogen atom goes to the less substituted carbon, which is the secondary one. And then we have the tertiary carbon, which will be a carbocation. It will be missing one bond. And here we have, since we have the nucleophile bromine, which is electronegative, and we have the carbocation, which is positive, what's going to happen is that the bromine atom will attack the carbocation. It's the nucleophilic attack. And then it will be linked to this carbon here at the end. So this is the product of this reaction. We have the bromine atom on the most substituted carbon and the hydrogen atom on the less substituted atom. We don't need to draw the hydrogen here. And since this carbon is not chiral, it has a bromine atom and a methyl, and the same if we're going this way or this way, the same the same bonds. So it's not chiral. We don't need to worry about stereochemistry in this case. Here we have another reaction of an alkene with HCl. In the first place, the double bond of the alkene will act as a nucleophile and go grab the hydrogen. And then in this step, which is the slow step, the chlorine atom will act as a leaving group since it's leaving. Here it is. The second step of this reaction is the formation of the carbocation. According to Markovnikov rule, the hydrogen atom goes into the less substituted carbon, and the chlorine atom goes into the most substituted carbon. Since here we have a primary carbon and here we have a tertiary carbon, it's obvious that the hydrogen atom goes into this carbon here and the chlorine atom will attack the carbocation. It's obvious that this is the carbocation. The carbocation, it's always the most stable carbon. So here we have the chlorine atom, which is the nucleophile in this second step, will attack the carbocation and will be bonded to it. Here it is. So this is the final product for this reaction. Since it's not a chiral carbon, since we have a methyl group, a methyl group, a methyl group, and chlorine, we have three similar atoms bonded to this carbon here. We can say that it's not chiral, so we don't worry about stereochemistry. So let's move to this reaction with iodine this time. We have, as we said earlier, the double bond always in the first step, which is the slow step, act like a nucleophile and grab the hydrogen. And the halogen acts like a leaving group and leaves. Here it is. And then we have for the second step, the formation of the carbocation. Here we have two options, but according to Markovnikov rule, the hydrogen atom goes into the less substituted carbon and the iodine goes into the most substituted carbon. But here in this case, we have here across the double bond, we have a secondary carbon and we have a tertiary carbon here. So the hydrogen atom will go into the secondary carbon and will have a carbocation, which is the tertiary carbon. Always the carbocation is formed in the most substituted carbon. And here we have nucleophilic attack, which is the second step. The iodine will act as a nucleophile and attack the carbocation and will be bonded to it. So the final product for this reaction is this molecule over here with the hydrogen here. We don't need to draw the hydrogen since we have hydrogens all over the molecule. And here we have the iodine bonded to the tertiary carbon. But here we have the carbon which is bonded to the iodine is chiral, since it's linked to the cyclopentane here and to cyclohexane here, so it's chiral. In this case, we have two products. The first product is the iodine going toward us, like coming toward us. And for the second product is the iodine going to the back of the page. The reason for that is that the tertiary carbon here, when we have a tertiary carbon, the iodine can attack it from this side here or from the back of the page. We have two main options. So it's going to be 50% for the first structure and 50% for the second structure, making it as a racemic mixture. So when we have a chiral carbon, we always have to think about stereochemistry. So we have another reaction of an alkene with HBr, but this time in the presence of an alkyl peroxide. We used to see reactions between alkene with halogens in the presence of water, but this time with the presence of an alkyl peroxide. Usually we apply the Markovnikov rule when it comes to hydrohalogenation reaction, but this time we are applying what's called an anti-Markovnikov rule, meaning that when an alkene is reacting with a halogen in the presence of an alkyl peroxide, a COOH for example, the hydrogen atom is bonded to the most substituted carbon and the bromine atom is bonded to the less substituted atom. We'll see it together. So here we have this molecule losing one bond, since the double bond will act as nucleophile and attack the hydrogen, and the bromine atom will act as a leaving group and leaves. Here it is. And here we have, since we are applying an anti-Markovnikov rule, the bromine atom, which is the nucleophile, will attack the less substituted carbon. Which one is the less substituted carbon? We have here a primary carbon and we have here a tertiary carbon across the double bond. So the bromine atom will attack the primary carbon and the hydrogen will be bonded into the tertiary carbon here. So we have the bromine atom over here. At the end of the reaction, we have the bromine atom over here and the hydrogen over here. Since we have the bromine atom linked to this carbon, which is not chiral, we have two oxygens and a bromine and another bond. We don't have to worry about stereochemistry. It has just one way to attack this carbon. So we have another reaction of an alkene with an HBr. In the first place, the double bond will act as a nucleophile and attract the hydrogen. Since here we have, for the hydrogen, we have a partial positive charge, and for the bromine atom, we have a partial negative charge, meaning that the bromine atom is pulling the electrons of the bond toward it. So the hydrogen will be attracted by the nucleophile here, which is the double bond. It attracts the closest positive charge, which is the hydrogen here. And this is the first step, like the hydrogen is attacked by the nucleophile and the bromine atom will just leave. This is the first step. And for this, the second step of this reaction, we have the formation of the carbocation. Since we have here a Markovnikov rule which says the hydrogen atom will attack the less substituted carbon, which is this one, and the bromine atom will attack the most substituted atom, carbon. So here we have the hydrogen, and here we have the secondary carbocation, which is formed after losing one bond. But here, since we have the option of making it more stable, but like by doing what's called the hydride shift here, since here we have a hydrogen that will shift into the secondary carbocation and make it very stable, like it won't need any bond, but we'll have a tertiary carbon here which will lack one bond, making it as a tertiary carbocation. So here we have a tertiary carbocation. And then what will happen is that the bromine atom, which is the nucleophile, will attack the tertiary carbocation and will be bonded to it. So we'll have a bromine atom here. But since this carbon is a chiral carbon, since it's bonded to So let's work on this final example here. We have an alkene reacting with an HBr. In the first place, the double bond will act as a nucleophile and go grab the hydrogen. The reason for that is that when we have lone pairs, it's partially negative. And here we have the bromine atom, which is very electronegative. It's partially negative, and the hydrogen is partially positive. So the double bond will attack the hydrogen, and the hydrogen will be bonded to it, leaving the bromine atom behind. So the bromine atom will act as a leaving group and leaves. This is the first step. The second step for this reaction is the formation of the carbocation. Since we lost one bond from the alkene, we'll obtain an alkane here. And according to Markovnikov rule, the hydrogen will be bonded to the less substituted carbon. Here we have a primary carbon, and here we have a secondary carbon. Since we have a primary and secondary carbon, the hydrogen atom will be bonded to the primary carbon, and we will have a secondary carbocation. But since we have the option of making it more stable by doing what's called the hydride shift, here we have a hydrogen that will shift into the secondary carbocation, making it stable, like having 4 atoms. But the tertiary carbocation here will lack one bond, which used to be the hydrogen, and then will be positive. So this is our final carbocation. We always have to look for the most stable carbocation. We have the tertiary is more stable than the secondary, and the secondary is more stable than the primary. So here is the final carbocation. And since we have the positive charge and negative charge, the bromine atom will act as a nucleophile and attack the carbocation. So this is our final product. We have a bromine atom here. But here we have a chiral carbon, since it's linked to a CH2CH3 from this side, CH2CH2CH3 from this side, and a bromine atom from this side, and a methyl group from this side. So this is a chiral carbon, meaning that according to stereochemistry, we have to draw both the racemic mixture, both the options of the racemic mixture. So the bromine atom can go from this side and attack the carbocation, and can come from behind and attack this carbocation. So we have this option, and we have the second option over here. We have 50% for this one and 50% for this one. That's what's called racemic mixture.